All right, welcome in. Okay, we better get started. Hi, welcome to my channel. I am Professor L, and yeah, we're doing a math live stream Thursday night. Hope everybody's doing well. Um, yeah, so I'm going to continue working on systems of linear equations using matrices. So if uh, if everybody's ready, we'll go ahead and get started and see how it goes. I am going to try to solve a system with three variables tonight, and um, I did a little bit of homework. I practiced one earlier, and then I didn't even like it wasn't one of them that was in the back of the end. It was not in the back of the book. So I rehearsed the method once, and I didn't really even have time to do that, but I did. And then I ran out of time and didn't have time to practice one that had a solution, but I feel confident so in the method. So just see uh, how it goes. Again, it's been a really long time since I have um, visited this topic of matrices, and this is kind of my math moment of the day that I get to hang out and do math, and then also critique myself later. So just being aware, I don't have a mirror when I'm teaching, so it's important for me to be able to reflect on my methods and how I'm interacting, what I look like up here, and so I'm just trying to pretend like I might have some students in the room and yeah, and hang out and do some math. Hopefully, somebody out there's watching and needs to know how to solve a system of linear equations with three variables. And if you do, hopefully my method is pretty straightforward. And if not, let me know and I will work on it. But let's see how it goes. All right, so I have this system picked out. And I just realized that I didn't get the solution out of the back. So I am going to go ahead and write the system up here on the board. And then what I'll do is I'll pause a moment. I'll go get the solution so that we know that we worked it correctly. Again, it's the means to an end, and there's multiple ways to solve it. So we've got x minus y plus 3z equals 3. And we have 2x minus y plus 2z, and that equals 2. And then we have 3x plus y minus 2z, and that equals 3. So there's our system. And I'm going to go ahead and just look this solution up real quick because I purposely picked this problem because it was in the back, but then I didn't go and actually write the solution down. Rookie mistake. And let's see. Of course, when you're on camera, you're filming yourself, it's like inevitably it's stress and pressure, but I'm trying really hard to not put myself under pressure. Yeah, that was chapter 1. It was 1 because it was just the systems. So it was 1, problem number 10. Hang on. Okay, so it was 1110E. Here we go. X equal 1, y equal 4, and z equal 2. So we'll put this at the end here. One, 4, 2. All right. And I always run a risk when I'm working something for the first time on the board, but it's not about me being perfect or trying to, look like an expert up here. Really, I just want to be a normal human being up here just hanging out doing math. All right. And if anybody is out there and wants to hang out and do math with me, you're welcome to do that. All right. So what I want to do first, so it's the same formula and it's almost the same method, only with a 3x3 it looks different. So we'll go ahead and put the formula up here. And what we're doing is we're using the inverse to solve the system. And I really like this method of solving. So it's not the only way to use matrices to solve. However, it's a much more straightforward method. So maybe we'll get into the Gauss-Jordan elimination method. But that one it's not my friend right now. So I might need to practice it a little bit more. All right, so we have this. We have A equal, so say we have a matrix and it's a 3x3. So we'll just say A and it's row 1, column 1. And then this would be A, row 2, column 1, and A, row 3, column 1. And then you have A, row 1, column 2, A, row 2, column 2, A, 3, column 2, A, 1, column 3. It's row 1, column 3, row 2, column 3, and row 3, column 3. And here is your 3x3 matrix. So you have this matrix. So your A inverse equals 1 over the determinant of A times the adjoint of A. And so this adjoint thing is what I was practicing earlier today to calculate that 3x3. And my linear algebra book is really looking like a foreign language, most of it, but some of it is making sense. So I'm just trying to push through it and remember all of that stuff that I learned so long ago. Yeah, so I'm pretty confident with this. And then if we're going to go ahead and turn this into a coefficient matrix and a constant matrix and the variables. So we're going to turn it into a different form. It's not quite augmenting it. I'm refamiliarizing my definitions in linear algebra, but what we are is we're going to turn it into a matrix of just the coefficients. And it's going to look like this. So it's going to be, so we've got, remember if it's just X alone, there's a hidden 1. So we've got a 1 there, a 1 here, a 1 here, a 1 here. So we can go ahead and put those in there so it makes more sense. But it's 1, -1. The sign goes with it. And so it's just the coefficients of your variables. And so we have 2, -1, 2, and 3, 1, -2. Okay. And that doesn't look straight. I can do it a little bit better. Since I've been doing this live stream, I've all of a sudden prefer writing in pen now. And I think it's because when I'm working on my math alone and my clipboard, I want to use a pen, but then it's hard because the pen does not erase as well as the pencil. But I'm more comfortable with the pen now. I think it's because I've spent so much time writing on this board. And I do the majority of my work on this board, so it's almost like now I want to use a pen, but I used to really like my pencil, so that's kind of different. All right, so we're going to multiply our coefficient matrix by our variables. We have x, y, and z. And then that's going to equal your constants. 3, 2, 3. And this is kind of how you're supposed to set it up. And if you have it in this form, then you can say that here's your solution, x, y, z is going to equal your inverse, so the inverse of your coefficient matrix, 1, 2, 3, -1, -1, 1, and then 3, 2, -2. So it's this inverse. 2, looking like an upside down 6 to me. So we've got -1, and then that is notation for inverse. So we're just saying the inverse of this matrix times your constants. 3, 2, 3. Okay. And all right. So we have to find the inverse in order to solve. So that's where this formula comes in. And what I'm going to do is I'm going to first calculate the determinant. And the determinant of a 3 by 3 is a little bit, it's the same process as the determinant in a 2 by 2. It's just more operation. What am I looking for? So I'm going to really try to organize my board so I don't have to erase anything, because that determinant, it takes up a lot of room. And so what you're doing when you're calculating the determinant, basically it's the dot product of the diagonals, but you subtract them instead of add them, basically. If I had to explain it in a nutshell, but we'll see what this method, I'm sure there's a more formal method. All right, so we're going to take our matrix, this one, and we'll call it A. And we're just going to write it out. 1, -1, 3. And I got to stay really organized, making sure my rows and my columns are neat. So that's a 2, -1, 2, and 3, 1, -2. And here's your matrix. So this method requires copying the first 2 rows over. So I'm just going to repeat these 2 rows here. So it's going to be 1, -1, 2, -1, 3, and 1. And so now what we're doing is we're taking the diagonals. So we're going to go the positive direction, 3, and then we're going to go the negative direction, 3. Perfect. And so what we're going to do is we're going to do the dot product of these numbers. So it's 1. So it's 1, -1, -2. So it's 1 times -1. Times -2. And we'll figure out what that is. It's 1 times -1 is -1 times -2 equals 2. So we've got 2, and then we're going to say plus. So we're going to do these now. -1, 2, and 3. So we have, so that's going to be plus -1 times 2 times, and you can't see what I'm writing, so I'm working on that. I'm trying to write off to the side. It's not natural for me. So it's something I have to learn to do. All right. So we have -1 times 6. So it's plus a -6. So we'll just leave it like that for now. So we've got this, and we got to do one more. So we've got 3, 2, and 1. So this is plus 3 times 2 times 1. We just use parentheses, stay consistent. So 3 times 2 is 6, times 1 is just, so that's plus 6. So we have this, and now we're going to go the negative direction, and we're going to, so we're adding all of those, and then we're going to subtract all of the other diagonals, so all the rest of them. So that's kind of in essence the method of doing it. So we've got 3 times -1 times 3. So we might do those here. 3 times -1 times 3. And so 3 times -1 is -3 times 3. So it's going to give me -9. And we're subtracting that. So we're minusing a -9. So then we're going to do that second diagonal, which is these 3. 1, 2, 3. So it's 1 times 2 times 1. And so that's 2 times 1, which is 2. So it's -2. Because remember, we're adding the positives and subtracting the negative diagonals. All right, so we have one more. It's this one, -1. Wait, did I do that right? Oh yeah, 1, 2, 1. So I've got -1, 2, and -2. And I am a little rusty on this method, to be honest. 1 times 2 is -2 times -2, and -2 times -2 is negative, or +4 rather, +4. And so we're going to subtract 4. And so after we figure out all of these signs, figure out what this equals, then we will have the determinant. This is and we'll go ahead and label this as determinant. If it's 0, then the matrix does not have a solution. Or wait, it might have a solution. It doesn't have an inverse. You can't invert it if the determinant equals 0 after you calculate your matrix. So you also need the determinant to calculate the inverse anyway. So it's always best to calculate the determinant first. All right, so we have 2. This is 2 minus 6 plus 6 plus 9 minus 2 minus 4 is -6. So those are 0. 9 minus 6 is 3 plus 2. It looks like it's 5. Possibly, if I did it correctly. If I didn't, I'll probably just work it out because I'm practicing the method, and then I'll work it again tomorrow. But I'm pretty sure that let's just look at it real quick. That's 0, 9, -6, 3. Yeah, I mean, it looks like solid like 5 to me. And that's one of the bummers of having to do math by yourself is sometimes it really pays to have somebody working with you and just going through the numbers so you're not alone. All right, so we have 5 for our determinant. So all right, so the adjoint of A, that is So that is a little bit more of a booger to calculate. So there's this thing called the transpose of a matrix, where you take and you swap out. So basically, I have to make a matrix of cofactors, and I don't know if I have room now. All right, we're going to try and squeeze it in here somewhere. But I have to make a matrix of cofactors, and using this one, and then I have to transpose it. So that's the hard part. Um, so how you do that, what you do is you take each individual one of these positions is going to have a mini matrix inside of it. And I really think I might be able to fit it in here. Let's see. So it's going to be kind of big. So we need as much space as we can. Oops. Better just take a drink. All right, so I am going to have to get a little bit more room here. Let's see if I can just get it in here. So a matrix of cofactors, C. And then we're going to transpose it. Why is this side always short? It's because I'm a lefty, I think. All right. I give up. I'm trying to get that. It doesn't matter that much. All right. So we're going to start with the very first position of 1. And we're going to multiply this mini matrix by 1. And then I've got -1. So I want to make sure they all fit in here. So I'm just going to write them all out. So we've got -1 times this matrix. And then we have 3 times this one. And that looks decent. All right, so then this one is going to have 2 times this one. Let's see if we can fit our third row in here. 3 times this matrix. And then we have -1. And this one is +1. And then we've got 2 here. And a little mini matrix. And then we have -2. And I'm going to try, I hope that we're successful, but I'm already thinking I want to do another one of these already. So it's probably what I'll do tomorrow. I know it's boring because it's the same, but it is what it is. So, all right. So how we going to build these matrices in here? We've got 9 of them, and make sure I've got my coefficients correct. So what we're doing is, let me see if I need another marker for this. We're taking the position that we're at. So we're going to start with this one, and we're going to cross out the rows and columns that this matrix is on. And so here's my matrix of cofactors. It's the remaining. So I've got -1, 2, 1, -2. And then I'm going to do the same thing. If I want this position next, then I'm going to cross out this row and this column, and my cofactors are 2, 2, 3, -2. Now I'm going to take this third position, and we're going to cross these out. So I have 2, -1, 3, and 1. Let's see if I got 2, -1, 3, and 1. Perfect. So we'll come over to this position here, and it's the second row. and first column. So we have -1, 3, 1, and -2. Wait, what did I say? -1, okay, -1, 3. And -2. Yeah, I wish I had a little bit more practice. All right, so -1 here in the middle. So we're crossing out the middle row and the middle column. So that's going to give me 1, 3, 3, -2. And then 2. This is also not the only way to calculate the inverse of a matrix. So you can use the Gauss-Jordan elimination method for calculating inverses. And honestly, maybe I'll try to do one of those next week. Who knows? All right. So 2. So we got 1, 1, -1, 3, and 1. Okay, and then 3, say 1. -1, 3, and 1. 3 here is 1, -1, 3, -1, 2. And then 1, I've got, let's see, 1, 1, 3, 2, 2, I think. 1, 3, 2, 2. Okay, and then one more. So kind of a painstaking process. We've got 1, -1, 2, -1. So make sure I did that one correctly. I'm just double checking because, right, 1, -1, 2, perfect. All right, so what we're going to do is we have to calculate the determinant of all of these and multiply them by a scalar. So I'm actually going to put this solution somewhere else so I can get some room here. So we'll write it up here. Okay. We know it's 1, 4, 2. And I don't know what happened when I was trying to write the 4. Okay, good enough. So it'll give me a little bit more room for my calculations here. So what I'm doing, and I'll try to do this as quickly as possible, the determinant of a 2x2 matrix is this same method, only you only have 2 diagonals. So it's -1. So this first one will be 1 times -1 . We'll do it like this. Let's do it like this, the dot. That way we can only have 1 parentheses. 1 times -2. Just do. I don't want to make it too complicated, so I'm not going to put a bunch of parentheses in there, but I still want to keep track of my order of operations. So we're adding this one and then subtracting. So it's 2 times 1. So we've got 1 times all that. So I guess we're going to need a bracket. So it's -1 times -2 is 2. And then that's minus 2 times 1, which is 2. So that's 1 times 0. So this first entry is just 0. Let's go ahead and write this new matrix down here. It's going to be kind of small, but we can fit it in here. So this is the one we're going to have to transpose. So that first entry looks like it's giving me 0. All right, so we're going to do this one now. Let's do this one. So it's -1. We'll use a bracket because we don't need that big of a bracket. Okay. So this is -1. So we've got this one, 2. So it's 2 times -2 minus, 2 times -2 minus 3 times 2. And it's -1 times, so -2 times, or 2 times -2 is -4 minus 6. So that one's giving me, it looks like a -1 times -10. That's going to give me a +10. So that was this next one, 10. All right, so let's do this one now. We've got 2 times 1. So it's 3 times 2 times 1 minus 3 times -1. So let's figure these out. So 3 times 2 times 1 is 2, and 3 times -1 is -3, times negative is +3. So 3 times 2 is 6. All right, so it's going to be 3 plus 5. It looks like 15. So this one will be 15. See if I can fit a 3 by 3 in there. And then this one here, we've got -1 times -2 is 2 minus 3 times 1, which is 3. Get a little bit faster with this. 2 times, let's see, -1 is -2. All right. So it's 3 times 1. And then -1 times -2 times 1, which is -2, minus 3 times 3, which is 9, is giving me -1 times -11. So that's going to be +11. And where are we at? I'm already wanting to take a mental break. All right, so we've got 2. It's just because I'm not used to doing the math. It makes me tired. Plus it's the evening. 1 times 1 minus 3 times -1. So we've got 2 times 1 times 1 is 1, and -3 -1 is +3. So 3 plus 1 is 4, times 2 is 8. So we've got 8. And we've got this one here. So we've got 3 times, let's see, -1 times 2 is -2. And that's minus -1 times 3. So I'm just trying to keep track of my signs. So I've got 3 times, let's see, -2, and that's +3. Because -1 times 3 is -3, and then times a negative would be positive. So I've got 3 minus 2 is 1, so it's 3, that one. And then we've got this one here, 1 times 2 minus 2 times 3. It's much more straightforward when you don't have negative numbers to deal with, but you have to deal with the negatives eventually, so it gets easier with time. -2 times 3 is -6. So that's 1 times -4. 1 times -4 is -4. And we got one more. We've got this one. So we're going to say -2. And we've got 1 times -1 is -1. And then we've got 2 times -1. So it's minus a -2. So that's -2, -1 plus 2. So it looks like it's going to be -2 times 1 for -2. All right. So after you have your matrix of cofactors, so this is your cofactor matrix. And this is what you're going to transpose. So the transpose process, you're taking your diagonal and you're leaving it alone. So you'll have a new matrix. It should be, the result should be the inverse. So we got 0, 11, -2. And then what we're doing is we're swapping out the symmetrical values along the diagonal. So 2 and 10 get switched out. So we'll say 10, that's an 11. And -2. 15 and 3 are going to switch places. So you have 15 and 3. And then you have 8 and -4 are also going to switch. So you have 8 down here and -4 here. And if my calculations are correct, okay, it's a lot of ifs, then this should be the inverse. A inverse. Wait, I have to multiply it by the determinant. Hang on. That's the adjoint. Sorry, I have to. Not quite. This is the adjoint. Sorry, I caught myself there. Adjoint of A. So for one more step in calculating the inverse, we have to multiply it by 1 over the determinant. So we have the determinant here. So each one of these values is going to get multiplied by the scalar. I am running out of room. At 1/5 times, we'll list them again. So 1/5, we'll just put it here, 1/5. What to do? Trying to learn how to be more organized. I'm just going to rewrite it. I'm not going to be lazy. Okay, 1/5 times all of these numbers. 0, -2, 3, 10, 11, -4, 15, 8, and -2. And then I got to figure out where I'm going to put it. I guess I could fit it up here. I can erase that, and I can fit it right in here somewhere. So 1/5 times 0 is 0. That's not going to change. 1/5 times 10. 10 divided by 5 is 2. 1/5 times 15, so 15 divided by 5 is 3. 1/5 times -2 is -2/5. 1/5 times 11 is 11/5. 1/5 times -4. Wait, we're gonna do 3 first. 1/5 times 3 is 3/5. And then you've got -4/5. And then 1/5 times 8 is 8/5. And then 1/5 times -2 is -2/5. So here's the A inverse. All right, so now what I need to do is I need to multiply my A inverse by my constants, because I have this. I am going to go ahead and erase these and put it right in here. Seems like the simplest thing to do. I mean, that's my scratch work anyway. So. All right. So we have 0. Let's see if I can write it where I'm not blocking the board. 2/5, 3/5, 2, 11/5, -4/5. We got 3, 8/5, and -2/5. So here's our matrix. We're going to multiply it by our constants here. 3, 2, 3. And we're multiplying a 3 by 3 and a 3 by 1. So remember the compatibility. In order to multiply your matrix, the columns on your first matrix must match your rows on your second one. And then the resulting matrix is a 3 by 1. So we'll have a 3 by 1 answer here. So we're taking this value, and I might have to erase some more. All right, so I'm going to erase some of this because I've got to do, it's kind of like the dot product. I don't know if it's technically the dot product, but it's very similar to that, what you're doing when you're multiplying these matrices. So it's going to be 0 times 3 plus -2/5 times 2 plus 3/5 times 3. So 0 times 3 is 0. This is going to be a -4/5. This is going to be plus 9/5. So -4/5 plus 9/5, that's 9 minus 4 over 5, which is 5 over 5, which equals 1. So this first position is 1. Now for the second position, we're going to take this row and this column. So it's 2 times 3 plus 11/5 times 2 plus -4/5 times 3. And see what that equals. 2 times 3 is 6. 11/5 times 2, that's going to be plus 22 over 5. And -4/5 times 3 is going to be -12/5. So we'll combine our fractions first. So 22 minus 12 is 10. So this is 6 plus 10/5. And so that is going to be 10 divided by 5 is 2. So that's 6 plus 2, which is 8. So the second position is 8. Wait. That can't be correct, because look, we did something wrong. What's happening here? Okay, 12/5, 22/5. Okay, let's say it's 8. All right, so it might be correct, it might not be. Because it says here it's supposed to be 4, and there is a chance I wrote it down wrong, and there's also a chance the back of the book could be wrong. So I'll have to sort it out, but the first one is correct. So let's see how we did on the third one. So let's see. 3. This row times this column is going to be 3 times 3. The more likelihood is that I've made a mistake, though, but that's okay. We'll figure it out. 8/5 times 2 plus, let's see, 8/5 times 2, negative 2/5 times 3. So 3 times 3 is 9. And 8/5 times 2 is 16/5. And negative 2/5 times 3 is negative 6/5. So that is 9. 16/5 minus 6/5, that's 10/5. So that's 9 plus 2 is 11. So I'm getting 1, 8, and 11. So I got my first solution correct. But according to the back of the book, it should be. All right, so I might have to plug this in and look at it. I don't know. I'll rewatch it and see what happened, and we'll revisit this one and possibly work another one. I felt like that was a little rough, and we did the method correctly. It is kind of, it's a long process, and quite dubious, if I should say. And I've been like on my board for 47 minutes now. So, okay, here we go. How to solve a system of linear equations using the inverse of a matrix. One method, there's multiple. And yeah, this is how you do it. This is one of the ways anyway, this method, using this formula here for the inverse. I might have made a mistake in my arithmetic at any point, and that's going to throw the solution off. But I will figure it out and revisit it. And you learn more from making mistakes than you do when you just work it correctly. And so I feel like if that's where I'm at, then so be it. All right. So it's Thursday, and since I've been lecturing now for so long, what I'll probably do is say goodbye for now and end the Thursday stream. And yeah, I'll just be back tomorrow. I've been having live streams since January now, and I haven't missed a Monday through Friday yet. I'm hoping, so I've got a good streak going, and so it's encouraging me because it's hard to keep. Sometimes you just don't want to show up if you don't have to, and so it's very good discipline for me to do it. And also, I think that I'm learning a lot and becoming more comfortable in front of the camera, and that's the end goal, because I just want to be myself, and yeah, just be able to hang out. And I'm obviously not there yet. So anyway, enough rambling for tonight. And if you watched my video, thank you so much. I really appreciate it. And you should come back and hang out with me sometime between 6 and 7 p.m. for now. And if I change, I'll put it in my description, and I'll post it for sure. Anyway, I hope everyone has an amazing rest of their Thursday. And yeah, I'll just be back. I'll say so long for now, and I'll see you next time. Bye.